Well, this morning we want to talk about graphs of other trig functions. We've done sine and cosine, those are the important ones. They're what goes into analysis of vibrations with waves and so forth, but these are of some importance, and you'll see them again, for instance, if you take calculus. You want to make sure that you know how to do these. So I'll put this as 3, meaning it's the third function we're going to look at. Suppose I want to sketch the graph of y equals a tangent bx minus c plus b. How do I sketch that? You might get a big clue from what we did with sine and cosine. What happened when we sketched a sine bx minus c plus d? What did we do? We started with the basic y equals sine x graph, right? And we stretched it and we shifted it. The a and the b cause stretches, and the x and y, we stretched it vertically by absolute value of a, stretched it horizontally by 1 over b, and then we did a shift of c over b, and a horizontally, and a vertical shift of d. Those are actually just all out of algebra, right? We started with the basic graph of the wave, and we just used algebra to shift it. We implemented it using absolute value of a as the amplitude, right? 2 pi over b is the period, and so on. But it actually just was an algebra stretch and shift of the basic graph of sine. We can do the same thing with tangent now. We can stretch and shift the basic tangent graph if we can just figure out what it is. So to sketch tangent, we're going to use the stretch and shift. Let's see how we can do it. Suppose I want to sketch y equals tangent x. Here's how I can get it. I'm going to make a table first of theta versus tangent theta. All right. And I can do that on the unit circle just like I did with sine and cosine, except I'm going to do it a little faster because we're very familiar with doing this from sine and cosine, right? The angle at 0 radians goes through the point 1, 0, right? The point at pi over 6 radians went through square root 3 over 2 a half, right? Because you can drop the perpendicular and make a 30, 60, 90 triangle. The point at pi over 4 radians, we recall, we dropped the perpendicular and got a 45, 45, 90 triangle. So this went through the point square root 2 over 2, square root 2 over 2. And the point at pi over 3 radians, we're going to do this all in radians, just like we did in sine and cosine, because those are where the applications are. Went through this point here at 1/2 square root 3 over 2, again, because we could drop a perpendicular and make a 30, 60, 90 here. And then finally, at 90 degrees, or pi over 2 radians, we went through the point 0, 1. What did we do with sine and cosine? We plotted the y coordinate here to get sine, or the x coordinate here to get cosine. We can plot the y coordinate divided by the x coordinate to get the tangent. So I'll say theta equals 0 radians. This one. Tangent is y over x. 0 over 1 is 0. So I can start plotting tangent now over here. If I have 0, 0, I'll just plot that here. I'm sorry, wake you up this morning. And now I can plot these other important angles. Pi over 6, pi over 4, pi over 3. I'm going to leave a little space and put pi over 2 down here with a dot, dot, dot in between. Let's see, pi over 6, again, I take y over x, 1/2 over square root 3 over 2. Well, the 2's cancel, they're both denominators. So this is just 1 over square root 3, also known as square root 3 over 3. That's a nice way to put it. To rationalize it. Pi over 4. Well, now I get square root 2 over 2. I'm at this point here. Square root 2 over 2, the y coordinate over the same, square root 2 over 2 for x. The tangent is actually equal to 1. What an easy one right there. I want you to make sure you know these values. The tangent of 0 is 0. This comes up in lots of applications, all right? So that's a very important property you'll see again later. And also, it's pretty important to know that tangent of pi over 4 is 1. Those are the 2 key values we want to be able to plot. All right. These other ones are useful to help sketch it out, but these you want to memorize in addition. pi over 3, let's see, the y over the x is square root of 3 over 2 over half. It's hard to write in here, isn't it? Again, the 2's cancel and you just get square root 3. Tangent of pi over 3 is just square root 3 exactly, right? And finally, pi over 2, I get 1 over 0 is y over x. Oh yeah, we recall that this is undefined at pi over 2, right? So how are we going to plot that point? There's a good one. This one would help if you had some calculus before, because in calculus you do limiting cases. You say, what happens is the angle theta gets closer and closer and closer to pi over 2, but never gets there. And you make this real rigorous in calculus. Here we can still do it intuitively, even if we can't prove everything. We say, what happens now if I take some larger angles in here, bigger than this? Suppose I took an angle real close to here, so if the perpendicular dropped down here, maybe at 1/10, 0.1. Well, this one is almost 1, right? It's kind of flat up here. It's almost a ratio of 1 to 1/10. The tangent y over x would be about 10, right? Almost 1 over 1/10 would be 10. Now suppose I take it real close here. Maybe now I've just got a little interval of 0.01. Well, this is even closer to 1, and so the ratio is about 1 to 0.01 is about 100. And by taking real skinny triangles here, I can make this ratio of y to x as big as I want. Can you see that? If I make this 1/1000th of a unit over, it's about a unit up, it's about 1 billion is the ratio of y to x. As big as I want. And so this gets bigger and bigger without bound. I'll just put in here, the ones that are being skipped are getting bigger and bigger just by that kind of argument that we make more rigorous in calculus. And so what we have is this. We plot the points over here. I've got 0, 0. I've got pi over 6, 1 over square root 3. So here's pi over 6, 1 over square root 3. I've got pi over 4, 1. That's a very important point. And then pi over 3, square root 3. Well, if this is 1 here, 2 would be about here, and square root of 3 is about 1.7. So here's about square root of 3. This one was 1 over square root of 3. So I've got pi over 6, 1 over square root of 3. Pi over 4, 1. I should put here. Let's see. Let's look right here. And then pi over 3 would be square root of 3 would be up here. And at pi over 2, we have no thing to plot at all, but the function gets bigger and bigger and bigger, so I plot it like this. And the graph of theta versus tangent theta looks like that. Now, I didn't use, in that graph, don't write this down, I wrote theta versus, this is tangent theta on this axis. I really want to graph these for the sake of following the textbook. I want to call this y equals tangent x. Couldn't use y and x there because I needed it for the unit circle, but if I call this x versus tangent x now instead of theta versus tangent theta, then I'm just plotting these points right here. And this is the graph. They get bigger and bigger, and right, going up arbitrarily high. So now what does the rest of the graph look like? It's actually not too hard to fill out the whole rest of the graph from this point. I want to do this because this really helps you to have some intuition how to graph some of these other things. We can plot a whole bunch more points. There's nothing intuitive about that, right? Instead, now also, we recall this property. Tangent of minus x is equal to minus the tangent of plus x. What was that property called? Remember? That's the odd property of tangent, right? If the minus comes out of a function, we call it odd. Just like in algebra. Remember in algebra you had, for instance, this function y equals x cubed. Oops. This is a side note here just to remind you. And it went through these points like 1, 1, and way up here somewhere 2, 8. What do you know about the graph of y equals x cubed? Maybe you remember it looks like this. Kind of flat here in the middle. I guess I should draw it flatter. It's an odd function too, right? Minus x cubed is the same is minus a plus x cubed. And it has this property. It also, for every point xy here, it goes through minus x minus y. That's true of any odd function. It has this symmetry through the origin. If this point is on the graph, then its sister point, minus x minus y, is also on the graph. The point 2,8 is on the graph. Down here, minus 2 minus 8 is on the graph. That's the defining property of an odd function. It has points symmetric through the origin. And that's true of tangent too, since tangent is odd. We use that odd property now to fill out the following. If it has an asymptote at pi over 2, it's also going to have an asymptote at minus pi over 2. And if this asymptote is approached up, this one's going to be approached down, and it goes through the same points over here. Here I have pi over, let's draw this one, at least pi over 4, 1, right? Over here, I'm going to have minus those coordinates, right? Minus x minus y. So this will be minus pi over 4 minus 1. And we can fill in these other points too, right? Pi over 6, 1 over square root 3 has minus pi over 6 minus 1 over square root 3 and so forth. But I'll say these are the kind of key points you want to draw. It's just like we had 5 points to sketch any sine function accurately, right? We wanted to sketch where across this midline, those 3 points, and then we wanted to sketch those 2 points where it's the peak in the valley. Same thing here, but we're going to use this. We're going to say it goes through the origin. That's a very important point. It goes through pi over 4, 1 and minus pi over 4 minus 1. And these 3 points are important to plot, and the asymptote. So it's sort of 5 things for both. This one, 3 points and 2 asymptotes. And those other points are nice for filling out the graph, but I don't worry as much about those. There's what the graph of y equals tangent x looks like by making this table for angles between 0 and 90 degrees. And then using the odd property to kind of flip this over and upside down, making it, since it's an odd function. Now there's one more property, and also the tangent of any angle plus 90 degrees, plus 180 degrees, pi, is equal to what? Does that look like a property you've seen before? Maybe not. We can prove it over here on the side. The tangent of x plus pi is the same as tangent of x always. This should look like what you saw before with sine. We had sine, for instance, don't write this down, x plus 2 pi equals sine of x, right? Because if you went around the unit circle 2 pi units later, you got the same direction from the angle, right? So coterminal angles have the same sign. Even better, sine tangent repeats every pi units. Here's why. It's because, using the unit circle again, if I now call my angle x instead of theta, suppose I take an angle x here, right? And I find the sine and cosine. Right? Well, I drop the perpendicular and take this coordinate over this coordinate to get the tangent. But I notice if I go the opposite direction on the unit circle, I just get minus the coordinates here that I got up here. So the ratio of this one to this one is going to be the same because the minuses cancel, right? If this is whatever, square root 3 over 2, and this is 0.5, then this is going to be minus square root 3 over 2 and minus 0.5, and their ratio is the same, right? Square root 3. So if this is x and this is the opposite direction, x plus pi, they have the same tangent, the same ratio of y over x. So tangent of theta is this one to this one. Tangent of theta plus 180 degrees more is the same ratio. So this, however, tells us how to draw the whole graph of the whole rest of the graph. This is what whenever x plus a number, the function at x plus a number is equal to a function at x, we say it has this period. It repeats every that many units. This says that tangent is pi periodic. Now I can get rid of this. This is an aside anyway. That is 1 tangent x, y equals tangent x, has period pi, repeats every pi units, just like sine and cosine repeated every 2 pi units. Now, if it has period pi, we know how to graph the whole rest of it, don't we? If you think about it. Because how far did we put between the asymptotes here? Okay? One's at minus pi over 2 and one's at plus pi over 2. They're pi units apart, right? It's pi from here to here, but it repeats every pi units. So we just take this whole thing and move it over. There it is. And where does it cross the x-axis over here? Did you figure that out? Repeats every pi units. It goes through here at 0, then it goes through here at pi. And if this is pi over 2 at this asymptote, and it repeats every pi units, this must be pi over 2 plus pi is 3 pi over 2. And similarly over here, if you go this way, there's another asymptote at minus 3 pi over 2. This crosses here at minus pi. And so what happens, I'll put dot, 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 it goes on forever repeating, just like sine and cosine, but now it repeats every pi units instead of every 2 pi units, because of this property of the unit circle. So it has this nice odd property that helps us to graph it. If we know this part, we just flip it over and down, and we get this part so that it's symmetric through the origin. Every odd function is like y equals x cubed. And then we repeat this over and over forever. And there's the graph of tangent. Okay. So it's very important to be able to graph this one. Know these 3 important points. Know the 2 asymptotes and then repeat. Now, what our initial goal was to be able to sketch any shifted and stretched graph of tangent, right? This will be the same graph, except by our algebra properties. It's a vertical stretch absolute value of a horizontal stretch 1 over b. Remember, if you put a bx here, then x only has to be 1 over b times as big to take the tangent of the same number. It's a shift of c over b horizontally, and a shift of d vertically. And so we can do the same things we did with sine and cosine to sketch this one. Let's move this over. To sketch y equals what we wanted at the beginning, a tangent bx minus c plus d. Use simply, we don't want to go through and figure out the stretch and the move over. We want to use the properties just like we do with sine and cosine, right? We want to do an amplitude and a period and that kind of stuff. Well, since this isn't a wave, but something that goes up and down forever, we don't call it an amplitude anymore. We'll call it a vertical stretch factor. It's the same thing, but it's not a wave, so you don't call it that. Vertical stretch factor, absolute value of a. All right? Because we're doing the same things that we did with sine. It's just algebra. It says whatever you multiply the function most makes all the y coordinates a times as tall, and flip upside down if a is negative. So if a is less than 0, then flip upside down. All right. So 1, 2. Well, how did we take into account the horizontal stretch with sine and cosine? We used the period, right? Only there's one difference, and this is the key point. This is the difference in the graphing strategy. The period is no longer 2 pi over b like it was for sine and cosine. Can you guess what it was? What it is now? Sine and cosine had period 2 pi, and the stretching factor was 1 over b when we replaced x with bx. So we stretch a period pi by 1 over b. The period is now pi over b instead of 2 pi over b. That's the trick. So otherwise, the graphing is exactly the same. You just start with that different shape, and you make the period only half as pi over b instead of 2 pi over b. So memorize this one is a little different, but the others are the same, right? What's the horizontal shift or phase shift? We can still call it. Since it repeats, we can still call it a phase shift. Periodic function. The phase shift is c over b. Just like before, right? And the vertical shift, if you add d to every y coordinate in any function, it just moves it by that amount. It's still a vertical shift of d. We're doing the same graphing strategies for this function as we did for sine and cosine. So we'll memorize exactly the same graphing strategy. I'll say it again. But we start with this graph and we have a period that's only half as much. All right, so vertical shift D. And there it is. The 4 letters give us 5 properties to memorize for this one. It's the same except for property 2. So here's an example out of the homework. Suppose I wanted to sketch this one with tangent. By the way, of these, it's just a little bit ahead. Of these 6 functions, we're going to find all their graphs. The sine and the cosine are extremely important because, as I told you, they're used in wave and vibration analysis. Tangent is pretty important, but not as much. The other 3 people don't use very much, but you will see them in some of your courses. So let's see. Suppose I wanted to sketch this one. Y equals 2 tangent pi over 3x minus pi over 4. How about that? And to tell you the truth, usually we don't have a vertical shift on tangent or cotangent or secant or cosecant. It's just sine and cosine because that tends to be where the applications are. So good chance you won't get very many vertical shifts on these. But you do just like you did with sine and cosine. You first pick off the 4 letters and then you use the 5 properties to sketch it, right? So I'll say A is whatever multiplies the trig function. B is whatever multiplies x. C is whatever subtracted, so C is actually plus pi over 4. And D is whatever is added on here. We can put a plus 0 and call D 0. And now from the 4 letters, I get the 5 properties. One, I do amplitude just like before, except I call it vertical stretch. His absolute value of A is 2. Right? The period, just like before, but except it's pi over B instead of 2 pi over B. So it's pi over 3. And again, you have to be careful on these. Rewrite this as pi over 1 over pi over 3. The pi's are both numerators, they cancel, and then 1 over a third left, it makes the period 3. So when there's a pi here in B, it makes nice whole, it gets pi out of the period. Okay, vertical shift period. Now I want vertical stretch period. Now I want the phase shift, the horizontal shift. The C over B, just like before, is pi over 4, what's subtracted over pi over 3. Pi's both being numerators cancel. And I've got 3/4 here. 1/4 over 1/3 is 3/4. Then I want my vertical shift. There's nothing added, so it's 0. And finally, is there a flip? No, because A is positive. And now I can sketch away. The idea is I just am stretching and shifting that squiggle shape for the tangent instead of the sine wave that we were sketching before. Okay. Just like before, because every point moves differently except for the shift point, the origin to the shift point. Right? The others, you shift them and then you stretch them also. Let's move the origin to the shift point and say 3/4 0 is the shift point. And I'll start there. That corresponds to what was the origin on tangent. Let's see if I can get this online. Here. And the idea is you say from the graph of the basic tangent, you just apply those techniques. The basic tangent looked like this. It was the origin, like with tangent x. It had these asymptotes at pi over 2 and minus pi over 2, and then it repeats. And now these basic points here are the origin, pi over 4, 1, easy one to remember, and its opposite point, minus pi over 4, minus 1, right through the origin. Now what we want to do is take that graph and think of shifting it so that what was the origin is here. This is the nice thing about tangent, like sine. It started through the origin, so now it's going to always go through the shift point. If it's unflipped, then I'm going to draw it up through the shift point like that. So I know how to start the graph. It goes up through that point. But here's the trick on tangent people like to use. Start at the shift point. By drawing the tangent through it. Up if it's unflipped, down if it's been flipped upside down by a negative in front. Then put asymptotes 1/2 the period on each side. That's what we have in the regular tangent, right? The period is pi, and you go half a period each side and draw the asymptotes. Put asymptotes half period each side. Of the shift point. So the period is now 3. I'll go 1.5 units over here. I'm sorry, 1.5 period. I'll go half a period from here. The period is 3, so half the period is 3/2. This point here must be 3/4 plus half a period. And then this point over here must be 3/4 minus half a period. Okay. So draw the tangent through the shift point, and then this will be an asymptote. Right. 3/4 plus 3/2. Well, you can add that up. This 3/4 plus 6/4 is 9/4. This one is 3/4 minus 6/4 is minus 3/4. And so we have an asymptote here, x equals 9/4. And here an asymptote, x equals minus 1/4. And I'll just sketch this up through here like that, down here like that. There it is, y equals twice the tangent of pi over 3x minus pi over 4. There's one thing that could use a little improvement though. See what it is, maybe? That's pretty good. I mean, the idea is it looks like this. It has a squiggle shape. It goes through the shift point. That's a very important point. But there were 2 other points that we said are kind of important. So is this really supposed to go like this? Did I scale it right, or was it supposed to go like this? How steep is it? That's where you use these points. If you go over halfway between the x-intercept and the vertical tangent, the vertical asymptote here, you should be 1 unit up on the unstretched tangent. It follows when you stretch and move this, that if you go halfway between this midline here, where it crosses the midline and the asymptote, halfway in between, well, let's see, 3/4 and 9/4, this must be 6/4 in here, right? Halfway between 3 and 9 is 6. 6/4, which is also known as 3/2, right? So this is the point 3/2 halfway in between. And if I didn't stretch it, it would be 1 unit up right over that, right? But actually I stretched it by a factor of 2, so it's going to be 2 units up. This is going to be the point 3/2, 2. This is the stretch factor. 2. And then because it was an odd function, I have to have some sort of symmetry. Halfway between 3/4 and minus 3/4, well, that's 0. I have to be down by the stretch factor. So I'm at 0 minus 2. And now I've got it. Let's draw these in green just to make the whole thing I've got asymptotes, x equals minus a fourth, x equals 9/4. I've got this important x-intercept at 3/4, 0. And I've got these 2 points here, 0, -2, and 3/2, 2. Let's call this 3/4, 0 in green. There we go. So now it's all in green. And I have one period of the tangent. A lot of the homework problems also sketch 2 periods of the tangent, so that's pretty easy. You can sketch the second one on either side, it doesn't matter, right? So let's sketch one more. Where would this asymptote go? Let's sketch the next asymptote. The idea is I'm just gonna take this picture right here and just slide it over and draw it again. I'm gonna draw this like this, down through here, exactly the same shape. Where does this cross? Well, exactly one period apart, right? The period is 3, so this has to be 3 units here. If this is 3/4, this has to be 3/4 -3. Have to figure it out, right? Is well, let's see, 3/4 -12/4 is -9/4. So this will be the point, -9/4, 0, and you can figure those exactly. I recommend when you do these things, on a test at least, try it on the calculator, because your graphing calculator is good at sketching these. Just make sure it's in radians so that it, because we're plotting in radians. But when you do, it won't tell you this exact point. Sometimes it's hard to figure out. Maybe you can't tell if it's exactly 9/4 or if it's some multiple of pi, right? Maybe it's -3 pi/4. But you can get these exactly by hand and then use the calculator to see if it looks about right. There's a second period. I just do one period over here to get this crossing point. And if this was x equals -1/4, I go 3 units this way. X equals -1/4 minus one more period, 3. Well, let's see, -1/4 -12/4 is -13/4. That's that asymptote exactly. If you can just draw again the 3 points and the 2 asymptotes for this one, and maybe sketch this x-intercept here and asymptote, then that's a good graph. And what happens is when you get good at these, you can kind of figure this in your mind just from the letters. It's a real nice device for having some intuition when you're solving later math problems with these things. You have an idea what the result is going to be like. Any questions on tangent there? Is that something to graph? Start with that basic graph of tangent, do the same shifting and stretching. It's just that it's pi periodic instead of 2 pi periodic. Well, these are going to go faster and faster because it's getting easier and easier, not because I'm going to try and make it harder and harder. How about if I want to plot a graph of y equals a cotangent bx minus c plus d? Guess what? A, B, C, D is the same stretching and shifting as before. We just have to know what the basic graph of cotangent looks like and do the same thing, right? And I'm going to show you a nice way to graph this. We're not going to go through and figure out points anymore on the unit circle. We can get this from tangent. So we're going to use this. We're going to use the graph of y equals cotangent x and just stretch and shift it again. With the same stretching and shifting method that we use for sine, cosine, and tangent. So we're going to start with the graph of cotangent. What does the graph of cotangent look like? And we can get it just like this. We'll say y equals cotangent x is also y equals tangent of pi over 2 minus x. How is that? Where do I know this from? We proved it before for triangles and said it holds it for any angle. How do I know cotangent x is tangent pi over 2 minus x? Does that look familiar? I hope. This is actually the cofunction identity, right? Cofunction, tangent and cotangent, sine and cosine secant and cosecant have this property that the cofunction in x is the function at 90 degrees minus x, or pi over 2 minus x. So this is what we call the cofunction identity before. We may have written it as cotangent x equals tangent 90 degrees minus x, but it's the same thing. So we know that property, and now here's another property. If I think of this as an angle theta, pi over 2 minus x, what is minus that angle? Let's call this minus theta anyway. I think of this a negative angle, pi over 2 minus x. If that's minus theta, I can think of this as tangent of minus x over x minus pi over 2. Right. This is the same. Then this is tangent minus theta. And tangent of minus theta is the same as minus the tangent of plus theta, right? That's the odd property of tangent. Tangent of minus theta is the same as minus the tangent of plus theta. But now I know exactly how to draw it. Do you see that? This is minus 1 times tangent 1x minus pi over 2 plus 0. It's an a tangent bx plus minus c plus d problem. A is negative 1, b is 1, c is minus pi over 2, and d is 0. I can sketch it. I can sketch cotangent entirely just knowing what graph a tangent looks like. So what is this? What does this graph look like? Now, from these letters, I observe that the vertical stretch is absolute value of A is 1. Right. Absolute value minus 1 is 1. There's no vertical stretch. It's exactly the same. You scale everything by 1. The period. Well, the period of this function is pi over b, we recall from tangent, right? Instead of 2 pi over b for sine and cosine, pi over 1 is still pi, so it's got the same period as tangent. Then I've got the horizontal shift or phase shift is c over b. Well, that's c is what's subtracted, so it's plus pi over 2 over b is 1. The phase shift is actually pi over 2. And then the vertical shift, there's no d on there, so it's 0. And then flip, yes, because A is negative. So we can sketch the cotangent, right? This is just another way of writing cotangent. We proved it with the cofunction property and odd property. We can sketch the cotangent by instead sketching minus 1 tangent x minus pi over 2 plus 0, which is the tangent function with these changes. So what we do is we first go to the phase shift, pi over 2, 0, right here. There's the shift point. Then how do you sketch tangent when it's stretched and shift? You start at the shift point, you go half a period each side to draw asymptotes, right? Remember that trick for tangent? This will help a lot on the homework. Start at the shift point, tangent goes through there. I'm going to go it down through because I flipped tangent upside down, so tangent now goes down through the shift point. Then I'll go half a period each side, so I'll go pi over 2, periods pi, I'll go pi over 2 to the right and left. And now this must be the asymptote x equals 0, and this must be the asymptote x equals pi. Right? Pi is the period, I go half pi each side and draw an asymptote. Now I know exactly how to draw it. I just draw it towards the asymptotes, each side. This is fascinating to me when I first saw it. The cotangent is exactly the same shape as tangent, right? How do I know that? graphing techniques. There's no stretches whatsoever. It's just shifted over pi over 2 units this way and flipped upside down. This is the y-axis here. So you shift it and flip it upside down, so it's the same shape. There's no stretches. And this is the basic graph of y equals cotangent. Got by stretching and shifting tangent. So remember that sine and cosine were exactly the same shape wave. All you did was take the sine and move it over pi over 2 units to get cosine. Similarly here, take cosine and move it over pi over 2 units to get sine. Similarly here, you just take tangent, move it pi over 2 units and flip it upside down to get cotangent. Same shape. That always helps me to know that, just to draw it the same. All right, so now I've got that. That will be our basic cotangent graph. Now, once you know that, to sketch the desired kind of graph, y equals a cotangent bx minus c plus d, simply shift and stretch this basic graph of cotangent. In other words, use the 5 properties. Of cotangent, and simply to sketch y equals a cotangent bx minus c plus d, simply use the properties of sketching with the letters applied to y equals cotangent. Now we should make a couple comments over here on the graph. It does, of course, repeat over and over because tangent did. What's this point right here where it crosses? What's that? I know this one, and I know its period is pi. Yeah, I just move over pi units this way, it's negative pi over 2. And I just repeat this. These are pi apart, so these are pi apart. This must be minus pi, right? And it goes on forever because tangent did. And you notice from this, once you sketch a couple of these, that that this has properties. I should draw it here, I guess. One, what's the period of this thing? Well, the period is still pi because tangent was, we just moved it over and flipped it upside down. The period equals pi. It now has, if I put 2 asymptotes. Where are the asymptotes this time? For tangent, they were at odd multiples of pi over 2, but for cotangent, since we shifted over, they're at multiples of pi. So asymptotes at x equals, so I better get rid of this. Asymptotes at x equals any k pi, where k we say is an integer, a number with nothing after the decimal point. K equals 0, 1, minus 1, 2, minus 2, etc. Any plus or minus whole multiple of pi. So the asymptotes are now at whole multiples of pi instead of odd multiples of pi over 2. And the x-intercepts are at odd multiples of pi over 2. Just because of that shift. So x-intercepts at x equals pi over 2 plus or minus a whole multiple of pi. There it is. And k is any integer. So these are good properties to know for cotangent. All right, and now we'll say, let's sketch one of these with cotangent. Let's move to the other side of the board, I guess. Let's do h here, 3h off the homework assignment. You can see how this works when you do it at home, hopefully. Sketch the function f of x or y equals -3 cotangent 2x. Let's write it in a little more detail. Minus 3 cotangent 2x minus 0 plus 0. And I recognize the number that multiplies the trig function is a. The number that multiplies x is b. The number that's subtracted here from dx is c. And the number that's placed at the end is d. I can sketch this with our graphing techniques using the 5 properties from the 4 letters, just like tangent and sine and cosine, similar to other trig functions. Let's say the tangent at least. We'll say the amplitude, the vertical stretch, again, since tangent and cotangent aren't waves, we'll call it a vertical stretch, not an amplitude. Vertical stretch, absolute value of A is 3. The period, again, for tangent, cotangent, will be pi over b instead of 2 pi over b, since their natural period is pi and you scale by 1 over b. So this will be pi over 2 will be the period instead of pi. The phase shift is c over b, just like it was for all the other trig functions. The only thing that's different on sine and tangent and cotangent is the period is pi over b instead of 2 pi over b. Otherwise, it's the same thing. So phase shift is c over b, just like before. Let's see, it's 0. All right, 0 over 2 is 0. And then the vertical shift, d is 0. No vertical shift. And finally, flip. Yeah, there is a flip because it's negative. Yeah. So that's all it's going to take. I'll just start with that basic cotangent graph. And again, move the shift point. Let me redraw it for online here. This was the basic cotangent graph. You don't need to redraw in the classroom probably. It went through pi over 2 instead of tangent went through 0. It has asymptotes at 0 and pi instead of minus pi over 2 and plus pi over 2. And then it has these points halfway in between. At halfway in between here, pi over 4, and the unstretched cotangent is at 1. Halfway between here at 3/4 pi, it's at minus 1. So there it is. The cotangent, the basic cotangent that we drew on the other board. Now we want to do this to it. We want to make the vertical stretch of 3, period, and so forth. Again, start with the shift. Start with the shift point. Oh, it's 0, 0. So what happens is whatever was on the origin before stays on the origin. Well, an asymptote went through the origin for cotangent. One asymptote will go through the origin for tangent because the origin moves to the shift point, which is still 0, 0. Now you, once you've got the shift point plotted, you go over one period to plot another asymptote. All right, period is pi over 2, so I'll just draw another asymptote here. And if this is at x equals 0, this is one period over pi over 2. Now the cotangent function goes through the point halfway in between, crosses its midline here. So the point halfway in between is in pi over 4. Cross that. And then what we say, we want to draw this shape, but since it's flipped, it has to go upside down. It has to go down, go up through the shift point instead of down through the shift point. So I'm going to sketch it like this. And then the last thing to say is how steep should it be? I've got a vertical stretch factor. What should it be? Well, again, on the regular cotangent, when you were halfway between the x-intercept where it crosses the midline and the asymptote, you went up 1 unit. That's the unstretched cotangent. So here, when we're halfway between where it crosses the midline and the asymptote, that'll be, let's see, pi over 8 is halfway between 0 and pi over 4. It has to be the stretch factor off, so this will be the point at -3. Pi over 8 -3, because the stretch factor was 3, it has to be 3 units down instead of 1. Similarly here, halfway between here and here, halfway between pi over 4 and pi over 2 would be 3 pi over 8. Between 1/4 and 1/2 would be 3/8. And it has to be up 3 units, the stretch factor. So that's it. That tells you how steep it is. So now I can put in some tick marks and put 3 here, -3 here, and fit it. There it is. There's y equals -3 cotangent 2x. Check it on the calculator. Again, it'll be hard to tell if this is the right point unless you scale your axes in units of pi. But you can get it exactly by hand. Again, the homework will say, oh, sketch 2 periods. So you can sketch another period to the right, another period to the left, whichever seems easier to you. I think it's easiest to go a period to the left, right? You just take this and flip it over like this, and the asymptote at pi over 2 becomes an asymptote at minus pi over 2. The crossing point here at pi over 4 becomes minus pi over 4. This is really easy this way, right? And you just draw the same thing again right through here. And I don't expect you to draw the 3 points in the asymptotes anymore. Just draw it to look the same. Look like it goes through minus pi over 4 pi. All right, so there's 2 periods of this cotangent. And then, well, it's like the sine and cosine. If you can sketch the graph from the equation, you want to be able to write the equation from the sketch of the graph. So there's some problems like that. And just like when you got a wave before, you could either rewrite it as sine or a cosine. Maybe you remember that from one of the tests. But by the way, I'll return the test soon. I'm waiting on some makeups. Yeah.
Is the shift point at the crossing point?
The shift point here was at this crossing point where it crosses the midline. Because the vertical shift was 0. I'm sorry. I misunderstood your question. Yeah, it's at the asymptote and not the crossing point. Yeah, this is the shift point here, 0, 0. Okay, so here is a graph you want to figure out the equation of a function from. Kind of a tricky one here, I think, 4b. The answer is not in the back on this one. So suppose I sketch this thing. It has this asymptote here. X equals minus pi over 6. Then I'll draw this one over here. X equals 3 pi over 6. The thing put suggestively, it's also pi over 2. And then it crosses through here at pi over 6. And goes like this. And then it crosses through here at -3. Looks like. Find the equation of this tangent function. By the way, I should mention today too, I sent an email, maybe a lot of you got it, but I'm having to shift my office hours from the moment over to online only due to some circumstances that have come up. So, I'll be happy to see you again today. I'll write on the board, but I just have to do it, remotely. Put it for a while here. All right, so find this equation, the equation of this tangent function. What is it? Again, you take now the 5 properties and get back the 4 letters, just like we did with sine and cosine. So it's the same kind of situation, just with a different shaped curve. So from the 5 properties, we'll figure it out, right? One, what's absolute value of A? The stretch factor, right? The vertical stretch. What is the vertical stretch? Yeah, because it goes, this one is halfway between the asymptote and the x-intercept, so this must be the stretch factor, is 3. Awesome. So if absolute value of A is 3, and then I'm just saying I'm shifting the tangent function. You can also use the cotangent flipped upside down if you prefer, but that's harder. Tangent's easier than cotangent, than flipping on top of it, who wants to, right? Like if I'm going to use a tangent function, y equals A tangent bx minus c plus d, then this is a right side up tangent, so it's unflipped. So A must be plus 3. So I've got A from the stretch factor and the unflipped part. Now, what do I notice also? I can look at the period, right? What's the period? Well, it goes from this asymptote to this asymptote at minus pi over 6 to 3 pi over 6. So the period is 3 pi over 6, the bigger asymptote, minus pi over 6, the smaller one, is 2 pi over 6, comes out to be pi over 3. There's just a little more room here. Period is 3 pi over 6 minus pi over 6. The difference in the asymptote is minus pi over 6. The difference in the asymptote coordinate is 2 pi over 3. But the period has to always be pi over b. Remember, for tangent, cotangent, pi over b instead of 2 pi over b. Well, let's see, if pi over b is 2 pi over 3, then I can divide it by pi and get 1 over b is 2/3. Evidently, b is 3/2. So there's b from the period. Now I can use the phase shift is pi over 6. The tangent usually goes to the origin, but it's been shifted over to pi over 6. So pi over 6 is the phase shift, which is c over b, just like with all the other trig functions. And now we know b is 3/2, so this is c over 3/2. Well, we multiply both sides by 2/3 and get 2/3 times pi over 6 equals c. Multiply both sides by 3/2, sorry. Cancel that. So let's see, c is pi over 4. I just have the 3's cancel, you get 2 and 2. There's A, B, C, and now the vertical shift, since the shift point is still on the x-axis, right? That's where we call this an inflection point, where it's kind of like a piece of a bowl shape down, it's bending over like this. Then it goes a piece of a bowl shape up, bending over like this. Where it shifts between bowl shape down to bowl shape up is where the midline is. It has an inflection point at there, we say in calculus. And so the vertical shift is 0. The way to deduce from that that d equals 0. So there's A, B, C, D, and now I just write y equals A tangent bx minus c plus d is y equals 3 tangent 3/2 x minus pi over 4 plus nothing. All right, so there's going back the other way, and then finally, we just have to do the last two trig functions. The nice thing is these are easy. Once you know how to graph sine and cosine, you can graph these easily. Show you how. This is such a nice way. I like the way textbooks tend to do these. So 5 will be y equals a secant dx minus c plus d. And what does the secant look like? You use the graph of cosine to get it. It's reciprocal. So what does cosine look like? Remember, it looks like this. A wave. And at 0, it's up here, and at 3 pi over 2, it's here, and at pi, it's pi over 2, it's here, and pi, it's here. Okay, and then 3 pi over 2 and 2 pi. So there's one period of the cosine function. And now you got secant of x. We can think of this. X secant of x is 1 over cosine. If x equals 0, maybe we remember that the cosine of 0 is 1, right? Here. 1, this would be minus 1. So the secant is 1 over cosine is 1 over 1 is also 1, right? If x is pi over 4, let's say, let's just do a few of these. What was cosine? Cosine was square root 2 over 2, you maybe remember, right? Or let's say 1 over square root 2 is cosine. And then the reciprocal of it is square root 2. So cosine of pi over 4 is 1 over square root 2. Secant is its reciprocal is square root 2. When theta equals pi over 3, right? Secant was, cosine was equal to half, and so secant is 1 over a half is 2. And we can do some more of those. At pi over 2, cosine is 0, secant is undefined. But in the meantime, it gets larger and larger without bound, just like tangent. And this is what you wind up with. And you just have to think I'm graphing a reciprocal of this wave, right? So at pi over 2, I have an asymptote. And at minus pi over 2, where cosine is 0 again, I'm going to have another asymptote. Wherever the cosine is 0, I'll get a 1 over 0 here, and the thing will, and the secant will head towards infinity or minus infinity is what happens. But where cosine is 1, the reciprocal secant is 1, and it actually just touches the peak of the cosine function. So there's the point 0, 1 that we plotted. And then pi over 4 square root 2 will be somewhere in here, halfway in between, right? Pi over 4. We should be at square root 2, which is about 1.4 here. Pi over 4 square root 2. And then at pi over 3, we should be up to 2, twice this height, right? So up here at 2. Get the point. Pi over 3, 2. And you can see what happens when cosine gets smaller and smaller, secant gets bigger and bigger because it's the reciprocal, right? When cosine is a 10th out here, secant is 10. When cosine is 1/100th, real close to this asymptote, secant is 100, the reciprocal. So this gets unboundedly large going through those points. And now we can get the whole thing, right? What does it look like over here, do you think? On this side. Well, you just flip this over, cosine lands on itself, so secant, its reciprocal should land on itself. It just comes up like that. It's a U shape up, just the reciprocal of this one. When cosine is small, secant is big. When cosine is one, secant is one. When cosine is zero, the thing heads off to infinity, right? And then similar over here, this is exactly the same shape as this we learned from the unit circle. So the reciprocal is exactly this one turned upside down also. We'll turn this upside down here like that. And it'll be another asymptote here. When cosine is zero, we'll always get an asymptote. Now what we notice is that secant is 2 pi periodic because cosine repeats every 2 pi units. And this is just its reciprocal. It has asymptotes. Well, let's see. Again, minus pi over 2, pi over 2, 3 pi over 2. Asymptotes at odd multiples of pi over 2. X equals pi over 2 plus any whole integer multiple of pi. Odd multiples odd over 2. Just like tangent. And then it has peaks, and it just touches the peaks and valleys of cosine. Peaks in the valley bottoms. That's how you draw it. Here's how I draw the secant anymore always. I just imagine the cosine function here and I make the secant touch the peaks and valleys. That's it, and have asymptotes where cosine is 0. I'm gonna put number 6 up here too at the same time. How about, you can probably guess, y equals a cosecant. Well, let's add one more comment here. Then use the same 5 properties for a sketch. Once again, you'll say this, and it's the same for all these vertical stretch factors, absolute value of A. All right, the period, since the original function was 2 pi, the stretch function has period 2 pi over B, just like cosine and sine. The phase shift is still C over B. You do everything the same as you did for sine and cosine. After all, it's just a reciprocal. And then the vertical shift is D. And you flip upside down if A is negative. And then finally, number 6, for y equals a cosecant, bx minus c plus d. You get this graph. You think of the sine function, which crosses a pi and 2 pi, and minus pi and so on, 0. And you think of, what if I took the reciprocal of this one? Well, it will have an asymptote everywhere the sine is 0. I'll call this y equals sine x. All right, because cosecant is its reciprocal. It'll have an asymptote wherever the sine is 0. It will touch the peaks and valleys like this, and you'll notice actually the cosecant and the secant have exactly the same shape too. U shape up, U shape down, U shape up, U shape down. Again, it's got period 2 pi. This time, because it's shifted over, right, the asymptotes are at whole multiples of pi, plus or minus. So period 2 pi, asymptotes, x equals k pi, the same as cotangent. All right, now as the last step here, for the few minutes we've got left, is to sketch these ones with the A, B, C, D in them. is very easy. It's just like these. You just, for y equals a secant, I wrote it over there, but bx minus c plus d, or y equals a cosecant bx minus c plus d. All you have to do is this, simply sketch the reciprocal function with the same letters. Cosine for secant or sine for cosecant. Two, put an asymptote where the reciprocal has an x-intercept, crosses its midline. Just like we do there in the basic function. And then take this U shape up and U shape down to touch the peaks and valleys. So you draw the sine and cosine and just make this touch the peaks and valleys and put asymptotes at the midlines, you're done. That's all you have to do to sketch secant, cosecant. They're not so hard after all. You just do it with the same letters. I'm going to do a quick example here then with a little bit of time we've got left. This is the least important of all of these because they don't come up as much. And again, they're usually not vertically shifted. The applications aren't usually there. It's just sine and cosine that are usually those. Suppose I wanted to sketch y equals 2 secant pi over 3x minus pi over 6. How would I sketch that? Instead of going to the 5 letters and sketching the basic graph, we'll sketch the reciprocal graph. We'll sketch first the reciprocal function with the same letters, y equals 2 cosine pi over 3x minus pi over 6, which we already know how to sketch very well, and then we'll just touch the peaks and valleys, right? And put asymptotes where it crosses the midline. So we'll start with that one, and we'll say, how do I do this with cosine? Leave some room here. There's a prescription. We'll say that the amplitude is absolute value of 2 is 2. The period is 2 pi over b. We've done this before. Is 2 pi over 3. Well, the pi's canceled. It's 2 over a third. Is 6 actually. The horizontal shift or phase shift for cosine is c over b is pi over 6. What's subtracted here, right? Over b is pi over 3. So it's 1/2. Vertical shift, there's none because d is 0. No flip since a is positive. And I just draw the cosine as usual, right? I'll do that. Start at the shift point. 1/2 0. Right there. That's the shift point. Cosine starts at the top. So now I draw the cosine. Now the guidelines, the amplitude is plus or minus 2. So I'll go up to 2 and down to minus 2. Draw the guidelines. And cosine starts at the top like that and comes down all the way back up like that. One period later is 6 units later. So this is 1/2 plus 6, right? One period later. Beginning here plus 1 period. Goes like that. And now how do I draw a secant? Having done the cosine with those same letters, I just draw a asymptote wherever the cosine crosses midline. I draw a U shape up to touch the peaks. And a U shape down to touch the valleys, and it's exactly like that. So I know these exact points very well. For instance, this one is at 1/2, 2, so this one is at 1/2, 2. This one would be, let's see, 3 units later, it'd be 7/2. Halfway between 1/2 and 13/2. This will be the point 7/2 minus 2. There we go. Well, it's out of time, but this is the secant function. I draw the cosine with the same letters and then draw the secant to test the peaks and valleys. Five of these problems in out of 6.2, 1 through 5, it's all but the last one, and it's just exactly what we did in class, so I hope that'll be a good start on that and bring in questions if you have them, right? Thank you, everybody. Good day.